Now, part 7, Tensor Algebra, Lecture 2, Multilinear Map of a Tensor 0s. This is, for this tensor 0s, this invariant, let's obtain the real R, the real scalar R, using the definition of the inner product in terms of slots. Recall that this tensor 0s is a multilinear map. What means that? You see, is a map S times this here, this space which belongs to the tangent vector space. Okay, it applies to the cotangent vector space and leads to the scalar R. So it takes S vector as input, S vector, not S covector. Now, it produces one real number as an output. You see the real number as output. It is a multilinear map between vectors VI partial xi, you see, and covectors VI dxi. Here, I is dummy, okay? Just to see the definition of vectors and covectors. And VI here is a contravariant component which belongs to the tangent vector space. This is a basis which belongs to the tangent vector space. But V sub I is they are the components of a vector which belongs to the cotangent vector space here. dxi is a basis, the basis vector, in this case, basic covectors, okay, which belongs to the tangent vector space. So there's I want this multilinear map between those two spaces. Now, local coordinates v, vij partial xij, vector that belongs to the tangent vector space. You see, I can express a tensor is invariant. I can express the same tensor in terms of the covariant components which belongs to the cotangent space, and there's a basis which also belongs to the cotangent space. Now, there's an inner product, okay, between Tp and V. Attention, Tp and V they are invariant, okay? I can express in any coordinate system. So, and this, the basis, using the basis covectors here, this Ti1 to Is, dxi1, okay? There's a tensor product, okay? And dxis, okay? So this is the covariant component which belongs to the cotangent space, and these are the basis which belongs also to the cotangent space. dxi, dxj are contravariant, you see, and because here is upper indices. Now, again, repeating here, down here, okay, I substitute the vector, invariant vector, it can be expressed in terms of the tangent vector space. You see, I just substitute over here. It's quite easy. So this is a tensor product, okay? Now, since we deal with multilinear map, see, I can set this T here and this V here outside the inner product, okay? So then I can write clearly that Tij, Ti, in this case, I1 to Is, okay? And V, I1 to Vs, I can express outside the inner product. Since multilinear map, you see, the name is saying, is clear. That's a linear map. okay? In this case, S multilinear map. S linear map, which is a multilinear map. So, and this here, I can work only on this inner product over here. Attention now, you see this inner product, the x1, okay, the partial x1 is a chronic delta, okay? So the xis, the product, partial derivative with respect to xis is also the delta, the chronic delta. So then the chronic delta acts on the v here, and the property of delta, or chronic delta, as you see. So I can write this, okay, as Ti1 to Is, V1 to Vs. Attention now, this T here, okay, they are components, covariant components belong to the cotangent space, and V over here are the contravariant component which belongs to the tangent vector space. You see, if you apply here the chronic delta, this is just see clear that this will be delta, chronic delta, okay? And now, the chronic delta, by definition, this we already used before, okay? So dxi partial xj, you see, you can swap, okay, the partial xj dxy, the inner product is delta ij. And the important problem, delta ij of a, in this case here, of ai, okay, let's put over here, you see? So delta ij, you see I here, this a, jj, you see, you have to substitute, and the a, jj. That's one property of the chronic delta. Now, the next lecture 3, we will derive an application for this particular case when S is equal to. So, the space will be, the tensor will be 0, 2. Okay, that's particular case. For you see a concrete example, just using all of this derivation displayed on this lecture.